All right, we're continuing our studies of fluid mechanics, and I'm going to move my notes a little bit closer here so that I can follow along with those. We are going to start diving into applications of pressure. Specifically, our goal is to build to one of our key ideas that kind of ties a lot of fluid mechanics together, at least for the introductory level. It's something called Bernoulli's equation. That's going to be a lesson or two later. It's going to combine a number of different ideas of different applications of pressure, would be the best way to describe it. And in this lesson, we're going to introduce we're actually going to introduce all three of the primary components that go into Bernoulli's equation, but we won't have enough time to actually explore all of them and to tie them together into fully an application of what Bernoulli's means and how to apply it for our fluid dynamic systems. Okay, but jumping in, this lesson is going to give us a lot of important information on pressure. Specifically, we are going to look at our pressure list. Now, in keeping with how I try and organize things, when we introduce something new, say back when we did forces, we had a force list where I gave you all the common types of forces that we would encounter. When we looked into energy, I gave you an energy list of all the common types of energy that we would interact with. And you may have seen it in other lessons because I find it a good way to kind of give you a one-stop shop where you can get information about the key things that you'll be applying here. So, we're building off of the basics that we had before from the introduction of just the basic pressure equation, which is a force divided by an area. That does kind of play into our pressure list, but we'll see that it mostly ties into conceptually how we would set up to get our reference pressure, I believe is the terminology that we would end up using. But there are three main pressure types that we will be looking at in regards to our studies here in introductory physics. Now, the notations on these might change a little bit over time and over the years. I'm going to try and keep something that is going to be most useful for what I think is a good approach. I'm going to do PR for the, I got to remember, I usually do reference, or I'm also going to refer to this as ambient pressure, not temperature. Pressure. This will be abbreviated P sub R for reference pressure. I'm using reference pressure because right now that is what the AP exam is actually describing it as, at least based off of the CED that I'm trying to realign these materials for. Okay, but this is the first of several of our pressures that we're going to take a look at, and normally how Bernoulli's equation, what we're going to build towards eventually, is written, it's usually the first one that you lay out. The next one, I'm going to use its technical term throughout my materials, which is the hydrostatic pressure. However, I'm also going to mark this as, and I'm going to put it in quotation marks, gauge pressure, because right now, at least according to the CED, gauge is tied specifically to what I know to be hydrostatic pressure. In this lesson, a little bit further on, we're going to talk about the differences between hydrostatic pressure and what I understand to be gauge pressure, though that doesn't necessarily align with, at least currently, the CED on the AP physics materials. Since this set of videos is for introductory physics and also a strong focus on the AP exams as we currently understand them, I am going to incorporate this terminology to try and have you cover your bases, for want of a better term. If the AP exam is going to refer to this as gauge pressure, I want you to be comfortable enough that you could draw that distinction, but I do not believe the way that hydrostatic pressure is laid out that it would be gauge pressure except in very specific circumstances. We'll talk about that soon enough. But gauge pressure, we will go, or not gauge pressure, hydrostatic pressure, as I'm going to call it, P sub H. And then finally, we're also going to talk about dynamic pressure. Though that one is going to be in another lesson for us to do a deeper dive into it. Dynamic pressure. In this case, we will go ahead and do that as P sub D. Now, this is actually a new notation that I'm incorporating, so hopefully this will work out well and we'll carry along with it. But in case I forget, it's something that I haven't done so much before, but I think is a good structure for us to actually tackle these with. Because now, since we're going to be talking about three different types of pressure that all combine to the net effect that we see with our Bernoulli's equation, I'd like to have a way in our notation that we could actually differentiate one from the other. So these are the three main types of pressures that we'll be talking about in our studies. Does that mean that these are the only types of pressure? No, and that there might be more Subtlety in applying these in a professional setting as you get to the higher levels or out into the workforce where they might apply these. So this also goes into, you may have people who work, say, in a mechanic shop, and maybe they're familiar with using a different term than what I have listed here. We're going to do the best that we can to try and best represent the materials, at least based on an introductory physics classroom approach. Okay, now that we've laid those out, we're going to take a deeper dive into them. We've already talked a little bit about the reference pressure. Reference, or I'm often going to refer to this as ambient pressure. In short, this is one where this is effectively the pressure out in which you're operating. So for the most part, I'm here in a room. I'm open to the atmosphere, and the ambient pressure would usually be, in fact, I'm going to write that down, usually, though not always, atmospheric pressure. This is basically wherever your experiment is set up or wherever you're trying to do your analysis, what is the common pressure that if we ignore any of the other things, like different weight of fluids or motion or anything like that, but just like sitting in a room here, what would the measurement be if I were to get out a barometer? In fact, we're going to talk about this one. Here's a little Bluetooth-enabled barometer that I got specifically for some of our studies here. If I had this activated and turned on my app, which I will soon enough, and read the reading off of it, what would it say my ambient pressure is? Now, normally, for simplicity, we'll say that it's 1 atmosphere, which is 101,000 pascals. I took measurements. Let me see where I wrote them. As of right now, in this room, under our current weather conditions, we're at about 96,000 pascals. So we're a little bit below the regular 1 atmosphere. Well, I'm still open to the atmosphere. We are not at sea level, so that's one of the things that would throw that off. Where I'm filming this is at about 1,000 feet, maybe 300 meters above sea level. So that's going to have an effect on it. And then also local weather patterns can have an effect on that as well. But that's why it's usually atmospheric pressure, especially for a lot of our experiments, because they'd be open to the air. Now, if this were a pressurized room, for instance, one of the rooms that I used to work in back when I was doing physics research was a clean room, and we actually kept that at a higher pressure than regular ambient outside pressure. Now, any experiments that we did in there, our reference pressure would be higher than 1 atmosphere. The idea was if there were any like open windows, or not that there'd be an open window, but any cracks in the door or anything like that, the higher pressure in the room would always push things out instead of bringing things in. As long as you're at a higher pressure on the inside, any opening will result in pushing things out. In fact, when we get to Bernoulli's, we'll talk about how our plumbing system is actually based around the same thing. So we'll come back to that. But my point on that is, any experiment that I would have done in that clean room, where it would have been kept at maybe 1.1 atmosphere, I would use whatever the pressure in that area was as my reference pressure, my ambient pressure. Okay. So this is one where you would go through, and usually you would probably not even solve for this. This would either be something that's given to you, or you would solve for using known values, or we would take a direct measurement of what our ambient pressure is. You could also have that this could be inside an engine of some kind for automotive or aircraft or something like that, and you might have in that part of the engine all the different subparts in the engine are at a higher or lower pressure depending on what their operating things are. In short, that's what our reference pressure is. Okay, let's see. I don't fully have an equation for this one. This one is in the Bernoulli's equation. We'd see it as the first P. Sometimes it is P naught. But a lot of times we're comparing 2 points, so you might have 0.0 and 0.1 or something like that. So I'm also going to use PR. In this, you can go through and you could, like I said, you would normally take a measurement of this, but you might be able to solve for this for a pressure based off of a force divided by an area to reference one of our previous lessons. Though this is not commonly what you would end up doing. A lot of times it's either given to you or it's a value that you end up solving for. We'll get a little bit more precise than that when we go into Bernoulli's equation in a couple of lessons and actually solving it. But this is why I refer to it more as the ambient pressure. It's kind of the pressure that everything is taking place in, and is your baseline, might be a good way of describing it. And therefore, it is your reference, the pressure from which everything else might be referenced. Now, this can be different than absolute pressure, which is often what we're actually dealing with, and we'll get to that with the gauge pressure. Okay, so there's that one. We're going to come back to this and unpack it a little bit more. But first, let's go through and introduce the other ones before we take a deeper dive into this. So, hydrostatic pressure. I'm using the technical term that I learned in my physics undergrad and also that I recall from any of my engineering classes as well. As I've said, as of the filming of this video, the CED for AP Physics 1 is describing this pretty solidly, unless I'm misreading it, as gauge pressure. I may be misspelling that because I'm terrible at writing out gauge pressure. In this case, I'm going to draw the distinctions between that, but what this term is actually supposed to represent, and the equation involved, is basically the pressure from the weight of a fluid at a depth into the fluid. The reason I'm making some distinctions on this is in engineering applications and talking with tradespeople and so forth, it is commonly accepted that gauge pressure can be a negative value. However, the equation that I'm about to give you cannot be negative. And so that's why I'm making a distinction between these two. My understanding is what I'm about to show you, the equation is specifically hydrostatic pressure, but that equation was identified as gauge pressure in the CED. Far be it from me to disagree with others, but I want to present it in a way that I think is consistent and agrees with all the things that I've encountered before. So, in this case, it's pressure from the weight of a fluid at a given depth in the fluid. So I'm going to give you the equation. So our hydrostatic pressure, which I'm calling P sub H, is equal to rho G H. P sub H is our hydrostatic pressure. And that name is actually very much specifically describing what we've got. Hydro for liquid, or more broadly fluid, and static. The idea of this is you're at the bottom of, say, a pool, but there aren't any like currents or anything like that. Say we're dealing with the pressure of the water pushing down on you in a pool. This equation would hold when the water is stationary. Things might change if the water's in motion, which will bring up our next type of pressure that we're going to talk about. Rho is once again the density of the fluid. G is the local gravitational field strength, or the acceleration due to gravity. For Earth, of course, this is usually positive 9.81 meters per second squared, or positive 9.81 Newton per kilogram. On my exams and the AP exam, at least as of the recording of this video, 10 is a good enough approximation, and most of the multiple choice and questions are solved assuming it to be 10. But remember, when we do a lab, real life is actually much closer to 9.8. And as a reminder, in every one of our equations, any equation that has little g, you always take the positive. We're taking the magnitude of the acceleration because we'll keep track of direction appropriately another way. In this case, h is vertical depth. We'll go ahead and put vertical depth. In the fluid. Basically, how far below the surface. And when we double back and do a deeper dive on these pressures, after I've given you the equations so that we can have those in our notes, then I've actually got an impromptu experiment that we're going to do as part of this particular lesson. And it ties to the CED and example problems that they've got. Okay, let's see. I do want to emphasize it is hydro, liquid, or fluid is the implication, and static in this case. So this deals with when the fluid is not actually moving, it's completely stationary. If you have it where the fluid is actually moving, there's a current of some kind, then this value could arguably change some, but what we're actually going to do is that's one of the things that Bernoulli's equation allows us to do. This is basically the pressure that is caused from the weight of the fluid above your head, basically how deep you are. In fact, if you look at this, rho, this is our mass per unit volume. We've looked at this before when it comes to our buoyant force. Remember, that was the buoyant force was equal to the weight of the fluid displaced, so we'd have like rho vg. In this case, we've got something similar where we've got rho related to the mass times g, so we've got something related to the weight, and then now we're dealing with how deep down we are. So the deeper you are, more weight on you, and that results in a higher pressure. In this case, there's no negative density so far as I know. This is a positive value, as I mentioned, by default. And our depth, in this case, you can't have a negative depth because if you are at a depth of 0, if h is 0, then you're actually floating. And if you try and go to a negative, where you'd be, say, above, I guess, a negative depth, then you're no longer in the fluid at all, and it wouldn't be having an effect on you. So in short, this equation, so far as I know, can never be negative, which is why I'm emphasizing that that doesn't jive with my understanding of gauge pressure, because gauge pressure can be negative. In just a moment, we'll go back through and take a look at those. However, we've got these here, so I'm going to fill in some units. Depth will be in meters. The acceleration due to gravity would be in meters per second squared, or Newton per kilogram, might be another way of doing it. And then our density is going to be kilogram per cubic meter. When we multiply all of those out, I'm going to go ahead and do that here. I've got kilogram per cubic meter. We've got times Newton per kilogram, which is another way of writing meter per second squared, times meter gives us the following. Oops. Okay, my kilograms cancel out. One of my meters cancels out, so instead of cubed, I have squared. Newton per meter squared, which is in fact a Pascal. So here's where our units end up working out. We're going to come back and talk about this one a little bit more closely in just a moment. I want to make certain that you have all of the equations for each of these. Our next lesson after this is when we're going to talk more in depth about dynamic pressure. In short, we're tacking reference pressure into this lesson because I don't have a whole lot to say about it. And it goes well with the hydrostatic pressure to set up the idea of what I understand to be gauge pressure. And that is going to take more or less an entire lesson time. Dynamic pressure will take about a lesson time as well and have some very different demos that I want to show with that. So that's going to be our next lesson. But I am going to make certain that here in your notes we've got all of this combined so that you've got all the info that you need. The best way of describing dynamic pressure is a description of the lateral pressure or the effect on pressure from a fluid in motion. I want to bring that up. Dynamics is a word usually describing to motion or things engaged in motion. Okay, so on this, here's a brief overview of that. We're going to talk more about that in our next lesson. But we have dynamic pressure is equal to 1/2 rho v squared. We're going to go through. We've got PD is dynamic pressure. I'm going to abbreviate that so we can keep moving. Feel free to write it fully out if you would like. Rho is going to be, once again, the density of fluid. Commonly water for us, but it could be all sorts of things. If you have a fuel injection system, you might be looking at gasoline, for instance, as it moves through your fuel injection system. So we've got V is going to be the speed of the fluid. In this case, as the fluid speeds up, we have an increase in our dynamic pressure, and that has a result on the lateral pressure off to the side. In short, the pressure in line with it becomes greater, and the pressures on the sides actually decrease. We're going to see some interesting applications of that. So dynamic pressure is describing the pressure effects from fluids in motion, and that's what makes it noticeably different than our hydrostatic pressure, which deals with not looking at motion, specifically trying to avoid it. So we've got V in meters per second. we've got fluid density, which is in kilogram per cubic meter. And then multiplying those out, we would end up with the following. We would end up with kilogram per cubic meter times meter squared per second squared. One of the meters cancels out, and we end up with, meter squared and meter cubed. We end up with the following, where it gets a little bit strange on this. So what I'm going to do is I'm going to make this just 1 and this 2. One of the meters cancels out, and we get the following: kilogram meter per second squared divided by meters squared, where this just becomes a meter squared instead of a meter cubed. In short, this is a Newton divided by meter squared, so we do end up with a Pascal. All right, so the SI units work out. Okay, so in our next lesson, we'll dive deeper into dynamic pressure. But let's take a look at some applications and understanding concepts of ambient pressure and gauge pressure, and then we're going to build with using the same equipment into hydrostatic pressure. I'm going to set up some demos on that, and I'll be back with you in just a moment. All right, so we're back. So we're going to take a closer look at this idea of ambient pressure, reference pressure, and how I think, or I'm pretty certain, it builds into gauge pressure by means of our hydrostatic pressure. And for that, I'm going to bring back in some of the materials that I had mentioned before. Let's see. So ambient pressure or reference pressure is commonly atmospheric pressure. So normally we might do the following. We're going to build towards something called the total pressure, and I'm going to start off with everything at rest. In other words, we're going to ignore our dynamic pressure on this. And for that, we would get the following: that we have our ambient pressure, our reference pressure, plus whatever our hydrostatic pressure is. Well, if we're not actually in a fluid at all, in fact, let me go ahead and open this up and bring up some of our settings. Maybe my pressure has changed recently. 245, no, it's still activated, it's still going. So this is actually a pressure sensor. I could get some other ones. I'm hoping to add some to my actual full lab supplies. This is just one that I bought that Bluetooth connects to my phone, and it's a little slow in its actual integration time. Like, I think it takes a measurement about every minute or so, but it is giving me usable information for some of my lab things. So I'm going to go through and actually show you. So I'm going to bring this over here. I've got a container, and right now what I've got for my atmospheric pressure, this thing currently reads 95,900 pascals. Now, as a quick heads up, I may write something down wrong a little bit. I'm stuck with the units that they've actually got programmed into this. So it was either inches of mercury, or it's actually defaulted now to millibar. So I'm having to do a little bit of math in my head, but millibar is fairly directly representative of the pascals, hopefully if I'm using them correctly. But I'm pretty certain that this is right. This puts us a little bit less than the standard atmosphere of 101,000. Again, this is being filmed at a higher altitude. We're about a 300 meter altitude above sea level, about 900, almost 1,000 feet above sea level, and that's actually going to have an effect on what our ambient local pressure is here. And it also is going to fluctuate some based on the weather patterns that are coming through. And full disclosure, this is in Oklahoma, so we have some very interesting weather patterns. So that being said, my current reading this is what I've got for our current atmospheric pressure. So here's what I've got. I'm going to set up a little container here. Now, I showed you in one of my previous lessons about the Magdeburg plates, where I actually put two of them together and then used a hand pump to actually bring them down to a lower pressure so that they held together. We assume that we basically pulled all the air out of there, and right now we're about to get some measurements on exactly how much air we did pull out. Because what I've got is, instead of another handle, this is actually a little chamber that came with a kit that I got years and years ago. I believe it's been discontinued, that's why I'm babying it. But I'm now going to take my pressure sensor and I'm going to put it into this container. Here's what I'm going to do. I'm going to seal this up. Okay, and then I'm going to take a little hand pump that I've got. I made some changes to the default container, especially recently, where I built in a few additional valves. But I'm going to hand pump this out. It's going to take a lot longer than it did before because I actually have a lot more air to try and pull out of this container. But I've got a good seal. It's starting to get harder and harder to do, so I think we're doing pretty well. Okay. I can try lifting this up. You can see that it's nice and good and sealed. And I've actually got a little valve here that I'm going to close so I can disconnect my hand pump so it's not just hanging off the side there. Because I've had problems with these breaking with having the additional stuff off the side. Now, my sensor just updated. It is now saying that we are at a new pressure of 300 millibars, so that's 30,000 pascals, or at least very close to that. Again, having some more dedicated equipment might get me a little bit better results on this, but we're working with the equipment that we have, and I think that this is still a good representation of exactly where we're at. So I've got this container, and I've got right now atmospheric pressure out here, and then much lower pressure on the inside. So my ambient pressure is the atmospheric pressure. And this is where we would end up with the idea of gauge pressure. So I'm going to talk about this specifically because what I've got is a container here. And originally I had my sensor, I'm going to hold it out here, and I found that the ambient pressure was about 95,900. Let's call it 96,000. 96,000 pascals. Okay, what you can do with your reference pressure is, this basically says, okay, if this is what the entire area is around with, I could approach this in one of two ways. I can either have this as the absolute pressure, which is what this thing is actually measuring, and then that would tell me, okay, the actual pressure, how much it's being squeezed, is 96,000 pascals. Or, here's where the reference pressure comes in, where we can then say, okay, what I'm going to do is I'm going to set this to 0. Okay, so if I go from room to room, or before I pressurize this, if I actually had the inside, before I sealed it up and closed it, then it would say 96,000 pascals inside and outside, because that's our operating pressure. That's where we're at. And then if I set that equal to 0, and this is commonly done with car tires, for instance. So if you've got the little gauge to actually check the pressurization of your car tire, where your car tire is not actually at 0 if it's flat, because it has air inside of it. Now that air just happens to be at atmospheric pressure, so it'll flatten out. So for instance, we've got this bottle, as we looked at before. It's not at a pressure of 0 on the inside, it's actually at a pressure of 1 atmosphere. I can squeeze it and it crushes just fine because it's not holding that pressure in any way, shape, or form. But it's not 0 pressure inside, it's 1 atmosphere inside and it's 1 atmosphere outside. If this were a car tire though, we would say that it has no pressure whatsoever because car tires are usually done in what's called gauge pressure. A lot of times gauge pressure is used when you're dealing with a pressurized system. And you're basically asking, what's the pressure compared to the surrounding area? So if I were to pressurize my car tires, mine go up to about 2 atmospheres. The inside pressure, if I put this in there, it would actually be at 3 atmospheres because it's measuring the absolute pressure. The reference pressure, if we take the reference pressure and set it to 0, this gives us what's called the gauge pressure. And the idea is a pressure gauge, a gauge is a device that gives you a reading. Mine right now says 300 millibar, if I'm reading this correctly. And that's what my gauge is saying. That being said, this is actually a gauge that's reading the absolute pressure. And hopefully I'm not confusing things too much with this, but the way to approach this is, we could then say the following. I could seal this up, and if I say my reference pressure is 0, I'm now going to say that instead of saying everything is 96,000 pascals, and that if I increase it by 100,000 pascals, then I would end up at 196,000 pascals. If we take our reference to 0, then we would get the following. We would start off with 0, we basically say it's not pressurized at all, and then we would raise it up to 100,000 pascals. We're basically saying, okay, this is effectively the same thing that we do with gravitational potential energy. I'm at an altitude of about 300 meters or so, but I don't have to add that on to every measurement that I do. I could say, okay, I'm going to make here y equals 0, even though it's a non-zero number, and I can measure anything above or even things below. Hence, why we can start to introduce negatives. So in short, I've got the following. There are two ways of looking at it. We've got our absolute pressure. Absolute pressure. And under the absolute pressure, we would have where zero pressure is, there's no particles hitting it, nothing pushing on it at all. Then the pressure inside here reads about 30,000 pascals. And the pressure outside is at 96,000 pascals. But this is the absolute pressure. If instead I were to look at the gauge pressure, 96,000 pascals. I would have the following, where this is reading something different, but because I'm setting the outside to 0 pascals, and making it my reference, I'm taking everything and reducing it by 96,000 pascals. So this would actually read negative 66,000 pascals. This is how you can get a negative gauge pressure. It's basically, we're taking the reference pressure and setting it to whatever our local is. So if you have something that is less than that pressure, pushing or squeezing less than that, then you end up with a negative gauge pressure. I don't think you're actually going to encounter this on the AP exam, but you might in engineering practices and your higher level classes. So I want to introduce this, and hopefully I've done it in a way that is kind of approachable. But this is why they're referring to it as the reference pressure. We could set it to just about anything that we want to simplify our calculations. But basically we set our 0 somewhere and we measure everything based off of that. That would be gauge pressure, for want of a better term. In this case, I try and deal with absolute pressure as much as I can, and there's not necessarily a downside to it other than it can make for a little bit more numbers that you would have to keep track of. One of the reasons why absolute pressure is not always used is because, again, with things like car tires and the sensors that we use along with them, sometimes the equipment that you're using can only measure gauge pressure. So it can be useful to be prepared for both of those in a practical, real-life application. Okay, we're currently at 30,000 pascals. I'm going to break the seal. We hear a hiss, and we start bringing it back up to atmospheric pressure. Now, this one's a little bit slow on the update, so it'll take a moment to actually do that, but we're getting set for our next thing that we're going to take a look at. So we are going to jump into the hydrostatic pressure. And that brings me to the next part that I want us to be prepared for. Okay, so this is actually very similar to one of the AP problems that they had, but I want to bring up at least some of the results of the lab that I did a little bit earlier. So this should update in just a moment, but here's what I've got. I'm going to wheel this over to the side. I've got a ballasted Ziploc bag so that I can drop this thing in water and keep it from getting just completely drenched. But here's what I'm going to do. I've got a large pitcher of water, largest container that I could easily find, and I'm going to take my pressure sensor and I'm going to put it down at the bottom of this. And then what I'm going to do, oh, there we are, we're back up to 96,000 pascals. I'm going to add a little bit of water onto it, such that we have a height, say from here, let's see, I'm going to go This is the top of my sensor, which I'm going to say is where the sensor is actually reading it. It's probably not exactly, so my numbers may not be precise. I don't know exactly where in my sensor. I believe it's getting input from here, but the sensor isn't just a barometer. It also has a host of other things like a thermometer and so forth. So I don't know where exactly the sensor is built in. But we've got a height here, and I could fill to different amounts. I could pour more water in, and we could measure to a height here, H. And here's where the H is showing our depth. This is how far our object is below the surface of the water. We can do one more, just for emphasis. And we could have here that this is another depth. Okay, so this is an experiment that we can go through and do. I'm going to show you the broad strokes of it, but I've actually already collected data on this. So here's what I'm going to do. I'm going to take the sensor, I'm going to put it into a Ziploc bag so that it doesn't just get soaked. I've also put some metal components in there so that I increase the weight of this so that it will sink. And I'm going to try and remove as much of the air as I can from this bag. Now, the air will be squeezed by the water just the same as the sensor and the metal will be, so it won't throw off any of those measurements. And here's what I'm going to do. I'm going to put it at the very bottom of this container, Out of the way, you. Okay, so it's at the very bottom of the container, and I'm going to turn on the faucet and add some water to this. Okay. Oh, okay, I didn't do a good job actually pulling all the air out of the bag. We've got it floating some, unfortunately. So ideally, I would have this at the very bottom. I had it set up just fine earlier. But this is what we could end up doing. So I could go through and I could take a meter stick and I could measure from the top of the sensor, let's say that it's down further, I would get about 6 centimeters or so, maybe 6.2 centimeters of depth. And so that's what we've actually got set up here. We can see now, hopefully this is updating appropriately, but we've got 96,100. We've gone up just a little bit in pressure. It was at 95.9, so we've gone up a decent amount. I'm going to go ahead and try and fill this up mostly with water. And we'll get a measurement of that, but I'll show you the data that I collected before actually setting up this video so that we would actually have good data to go off of. Now we've got our sensor down here. Hopefully I'm not taking on too much water, but this thing is marked that it's water resistant, so we're going to find out the hard way, I guess. But we're already up to about 97,000 pascals. But in this case, we've got the following. I could say that my pressure, when I have it filled this much, would be, my hydrostatic pressure would be rho GH. Well, that's rho G little h. So that was something like 6 centimeters or so, as we said just a moment ago. At this point, we've got something like maybe 15 centimeters. This were towards the bottom. We would have, yeah, about 15 centimeters or so. And as we increase the height here, we would end up with each of these getting bigger and bigger. So this might be 0.06 meters, 6 centimeters. This one might be rho GH. This one might be 0.10 meters, 10 centimeters. And then finally for my purple one, I might have pH is equal to rho GH, and this might be something like 0.15 meters. Rho, our density is going to be 1,000 for the SI units for water, at least standard water. Yeah, we're at about 97,000 is our actual pressure that it's reading right now. Just a little bit below that, 96.9, I think. And so we've got that. I'm going to wheel this over and set it aside for now. Hopefully everything's going fine with the sensor. But I don't want to get so caught up in trying to make that work live on the camera that we get distracted by some of this. So for instance, let's make a prediction. We're at about 15 centimeters worth of depth. Let's make a prediction off of this. We said that we would expect pH to be equal to rho GH. And filling this in, we would have 1,000 with appropriate units times 9.81 with appropriate units times our height of 0.15 with appropriate units. So in this case, the weight of the fluid above us is going to be 1,000 times 9.81 times 0.15 gives us our hydrostatic pressure comes up to about 1,472 pascals. So what is our total actual pressure? Now remember, my sensor is going to read the actual full pressure on this. That's the pressure from the weight of the fluid pushing down on the sensor. So I'm going to wheel this back in. So that's just from the weight of this water actually pushing down on the sensor. But that sensor is open to air, and remember the air is also applying pressure on the top of the water. Here's where we're combining those two pressures. We didn't have to worry about atmospheric pressure before in my sealed chamber because we actually separated it from the atmosphere, but I want you to remember that we've got air up here that is pushing down on the fluid no matter where it's at. So our total pressure is actually going to be our reference pressure plus our hydrostatic pressure. Well, our reference pressure, we said, was about 96,000 pascals plus 1,472. Let's call that maybe 1,500. 1,500 pascals. In this case, I don't think that we have more than 2 significant figures worth of precision on this. So we would end up with 97,500 pascals is what we would predict. Right now, I have a reading of, you may not be able to see it, I'm not even going to try, but 97,300.6. So we've got actual reading. Actual is 97,360 pascals is what this is reading. We're a little bit off, but we can see that this is actually working decently well. And this is our experiment. Now, this is once again very similar to one that is on the current CED for AP Physics 1. There are a few things that I want to bring up. One, I'm going to go ahead and show you the end results of the lab that I did in preparation for this, testing out all of this equipment. I have my depth. I poured out some of the water, so I did this in reverse, and then took measurements with my actual barometer. The important thing is this. We can see that we've got a prediction from dynamic pressure that we would have that our pressure, or not dynamic pressure, hydrostatic pressure, rho GH. If I have that this is my y-axis and this is my x-axis, then I would expect a linear relationship with this being the slope. In short, as h gets bigger, our pressure will get bigger because this is a constant, density of water, about 1,000 kilograms per cubic meter, or 1 gram per cubic centimeter, but we want to use the SI. And then G, well, here near the surface of the Earth, as long as I don't go super high or super low, should stay about the same at about 9.81. So since both of these are constants, we would have, as H increases, the pressure should go up by a similar amount. In fact, these are linearly proportional. So if I were to collect data on these and graph them, I should end up with, if I do a pressure as a function of depth, then I should end up with a line, the slope of which is equal to rho times G. So here's my actual data again, and I've set up my graph. So here's my depth. So when I had this completely full, we were about 18 centimeters deep. When I had it mostly empty, we were about 3 centimeters deep. And then here are the pressures that I got from each of those. And when I graph this out, we can see that we do have a linear relationship, which supports our equation. On top of that, I've done the equation of the line here. We ended up with 9,200 as our slope, which what we're actually expecting is about 9.81 times 1,000, 9,800. So I'm noticeably off, but then again, I'm also using a sensor that is probably slowly taking on water, and I should probably actually get that out of there here in the near future, which I will soon enough. That being said, here are some examples of applying and testing hydrostatic pressure, and here is data that I collected shortly before this video record. Okay, there are 2 last things that I want us to take a look at. I mentioned in one of our previous lessons that we would talk about the nature of atmospheric pressure, and that we underestimate exactly how much we're being squeezed by the atmosphere. So here's what I want you all to imagine. You all are used to being up in the air, and so most of us, myself included, don't even think about how much we're being squeezed by the air. But we do know that our pressure, our ambient pressure, our reference pressure, for instance, is about 101,300 pascals. That's atmospheric pressure. Okay, so my question is this. What if you were to dive in and go down to the bottom of a pool? How far down do we need to go in order to feel a new pressure that is, well, absolute pressure, 2 atmospheres, but gauge pressure, 1 atmosphere? That feels like 1 additional atmosphere squeezing our body. That way we can compare it. How deep do I need to go, in other words, for my hydrostatic pressure to be equal to 101,300 pascals? Ignoring the reference pressure, because if we added that in, then we're going to end up with 202,600 would be the total pressure, at least in absolute scale. So in this case, here's what I want. pH is equal to rho GH. We've got 101,300 pascals, with appropriate units, equals our density of our fluid. Well, we're dealing with water, so that'd be about 1,000 kilograms per cubic meter. We got 9.81 meters per second squared, or Newton per kilogram, and we get H. This represents how far down we need to be in order for the water in the pool to be squeezing us just as much as we're being squeezed by the air right now. Technically, we're actually doubling the pressure, but then that way we can compare it to what we're used to so we can get a clear idea of that. Okay, so with this, I can go through and I can solve for H. My calculator's over here. So I'm going to take 101, 300, divided by 1,000, and then divide it by 9.81, and I get the following. You need to go down about 10.3 meters. Let's see, so that is going to be somewhere on the order of about 30 feet. You need to go down about 30 feet of water. Now, if you're anything like me, you may have been down to maybe a 10, 15 foot deep pool. I haven't had access to a lot of 30 feet deep pool. Maybe your mileage may vary, maybe a bit different than mine. But even at 10 to 15 feet, I can really feel that water squeezing me. Well, you'd have to go even further than that in order to actually feel just atmospheric pressure. The only reason that we don't feel it, that we don't realize it, is because we've always felt it our entire life. So it's just kind of the standard. It's our reference pressure. So we kind of compare everything else to it. Okay, last thing that I'm going to bring up on this. Applying this in an hopefully interesting-ish way. In World War II, one of the mainstays of the United States fleet was the Vallejo class submarine. The USS Vallejo was one of the early ones in that field. But this one was one of our major classes that we had quite a few submarines on. On this one, I bring it up because submarines are one of the main things that are intended to dive deep beneath the waves. And I wanted to tie it to something realistic on this. We've got, in particular, the Vallejo class was a significant improvement, and that they used thicker, higher yield strength steel in the pressure hull skins and frames, which increased their test depth to 400 feet or 120 meters. So that's the main thing that I wanted to bring up on this. There's some old war movies that I've seen where they've got it where they put like a string across in the submarine, and then as it went down to deeper and deeper depths, as it got squeezed, you'd actually see the string bow some. So that's always something that's fascinated me. But in this case, we've got a Vallejo class submarine. And so on this, we've got the submarine near the surface, and it could go down all the way down to a depth of about 120 meters, at least with the technology at the time. So in this case, what I would like to know is, what is the pressure on the outside of the hull, specifically the hydrostatic pressure? We know that when we find it, we could add 1 atmosphere onto it because we've got an atmosphere's worth of pressure pushing down on the water. But in this case, we're probably going to find that that's significantly much smaller. In this case, rho GH. In this case, we've got pH equals 1,000 kilogram per cubic meter. G is 9.81, or 10, honestly, for the scale that we're doing, and 120 meters. So I multiply all of these out, and I get that the pressure that this thing could withstand came up to 1,177,200 pascals. Now I can divide that by 101, 300, and that gives me, this comes up to about 11 atmospheres, which isn't that surprising. We just found that about every 10 meters you go down, you actually add about an atmosphere on there. So if we do actually add the atmospheric pressure, we're going to find that that brings it up to about 12 atmospheres. Absolute pressure is what the submarine could actually tolerate. Though on the inside of the submarine, they're probably going to keep the pressure in there around atmospheric pressure so that it's at least comfortable for the crew. All right, so here's another application and demonstration of solving some applications of hydrostatic pressure. One of the last things that I'll mention on this, one of the other reasons that I like to bring this up, I guess I didn't actually bring up the page on it, but we have a decommissioned USS or Vallejo class, at least as of the recording of this video, in Oklahoma, over in, I believe, Muskogee. The USS Batfish has taken up permanent residence there. So if you're in the area and interested in that, check it out. It is now a museum ship. Okay, until next time.